So this is my second lecture for this magnetostatics. So till now what we have done, we have just studied about that moving charges produces current, which in turn gives you magnetic field, and we have found the direction of this magnetic field by using this right hand collapse rule. यसमा के गर्थ्यो भने मैले राइट ह्यान्डले चाहिँ टक्कै एउटा तार पक्रेँ अरे, बुढी अम्ला चाहिँ अर द थम इट्स पोइन्टिङ टुवर्ड्स द डिरेक्सन अफ ए करेन्ट, देन अरू अम्ला जुन चाहिँ ऱ्याप गरिरहेको छ नि तिम्रो कन्डक्टरलाई, द्याट विल गिभ यु द डिरेक्सन अफ यर म्याग्नेटिक फिल्ड. सो अल्सो अर्को के गर्यो भने हामीले when a moving charge is placed in a magnetic field, it will experience certain kind of deflection, so which in turn will give you force, and the force is given in this direction, and from that we find the definition of magnetic field induction as well, and also we got the dimension of magnetic field induction. So what are the objectives for today? These are the objectives for today's lecture. One is your Lorentz force, second is we will start with our Biot-Savart law, and we will apply this in some very special case, or in one of the case in which is a straight conductor carrying current. So let's start with the Lorentz force. So previously we have studied that the moving charge will experience certain kind of force when placed in a magnetic field. But in addition to this magnetic field, suppose if we have electric field as well, then the total force is given by QE, which is here coming from your electrostatics, and the additional field which is here magnetic field. So this total force is called a Lorentz force. So that's much for a Lorentz force. So how to find the direction of a deflection of this charge when placed in a magnetic field? This is given here by a Fleming left hand rule. So what does that tell you is, if you place here left hand fingers perpendicular to each other, this thumb, middle finger and your forefinger, बुढी अम्ला, बीचको अम्ला र यो forefinger, अब यो तीनटा अम्लालाई चाहिँ हामीले perpendicular राख्यो भने के हुन्छ, the thumb will give you the direction of a force, and middle finger will give you the direction of a current, and this additional forefinger will give you what? The direction of your magnetic field. So previously in this case, the current was in this direction, the magnetic field was in this direction. Now you can place a finger. So your middle finger will be in this direction, your forefinger will be pointing inwards, so the resultant thumb will be pointing on this direction, so it will give you a direction of the force. Now we'll start with the Biot-Savart law. So actually, suppose a wire, we have a straight conductor or some conductor which is carrying a current. Now it will what? It will induce some kind of magnetic field. Suppose we want to find the magnetic field induction at a given point. Suppose let's say at this point. So what does this law say is, the magnetic field is inversely proportional to the square of a distance. So further it is, the less the magnetic field induction will be. Closer it will be, more it will be by the power of square. So the direction is given by, as you can already know from your right hand collapse rule, the direction will be pointing at downwards. So the total magnetic field is given by a cross product of dl. This is here dl. Now if you consider a small line element, so always take the direction of the line element towards the direction of a current. So this is a cross product between this direction and this direction. So your total magnetic field will be given by the integration of I dl cross of r. R is a unit vector around this direction divided by r square. So dB is given by I dl sin theta, where theta is the angle between the r and dl. Now next let's go to our case, straight conductor at a given point, how much the magnetic field intensity will be, or the induction will be at this point P. Suppose we draw a straight line which is A, which is perpendicular to this straight wire, and this is the shortest distance between this point and this wire, which is given by A. Now we consider a small line element dl, which is given over here by a green line. So according to the Biot-Savart law, dB, or a magnetic field induction due to the small line element dl, is given by mu naught by 4 pi idl sine theta by r square, where theta is the angle between this dl towards the direction of a current we have taken, dl, and the vector r, this direction and this direction, this theta and this theta. Actually this is extremely small, so angle can be taken as theta itself. But over here what we can see are, there are three different variables. One is here dl, another is here r, and another one is here theta. Now what we want to do? Now if we want to find the total magnetic field induction, then we have to just integrate this. But how to integrate this? We have three different dependent variables. So now we want to reduce this number of dependent variables. As you can see, dl is also changing as this point is increasing. Theta is also changing as this keep on increasing, and also r square is also keeps on changing as it goes further and further. It will be longer and longer. So we want to reduce this to a single variable. Then after that we can finally integrate it. So let's just focus on this thing, small line element dl. Okay, so this was your conductor. Now I'd like to just isolate this. From there, this is your r, which is a distance over here, and this is a perpendicular which is drawn over here, perpendicular to this. Now I would like to just isolate this thing. I've just isolated it over here. You can see I've just isolated that, and I've rotated it in this manner so that it will sit like this. So you can see whether it's the same thing or not. If you rotate it, then you will again get the same thing, whatever it was sitting over here, the same thing. So basically I've just rotated it, so it will be easier for you all to see. Now in the next slide I've just zoomed it. Whatever was sitting over here, I've just zoomed it. Now it will be easy. Now this is your theta. So your sine theta will be given by h. I've just taken this as some h by dl. This is basically perpendicular by hypotenuse. This is a perpendicular, this is a hypotenuse. So h is given by dl sine theta. Now we want to find sine d phi. Now dl sine theta is already sitting over here. Now two variables we have kind of taken care of. dl is sitting over here, which depends on h. Now we want to define this in terms of d phi. Now sine d phi is given by perpendicular is h by hypotenuse is here r. As this d phi is extremely small, so we can take sine d phi as just d phi. So d phi is given by h. I have to substitute over here dl sine theta by r. So dl sine theta is given by r d phi. Now in a sense we have written dl sine theta in terms of phi, but we still have one more variable which is r. Now we just substitute that over here. We have this, previously we had this, and now we have defined dl sine theta in terms of sine theta in terms of r d phi. Now we have reduced the number of dependent variable. Now after substituting, what we will get? Dl sine theta as r d phi as ir d phi by r. This r will cancel out. So now we are still left with two variables. One is phi and another one is r. So still we have r and phi. So this we will do in our next lecture. So thank you very much.